In this problem, I have some linear quantities that I'm going to have to convert over to angular quantities using my radius before I can solve for some of my angular quantities. So if my angular velocity is going to be a ratio of my linear velocity to radius, and my angular acceleration is going to be my linear acceleration as it compares to radius, I can find those values so that I can use them. So 30 meters per second as it relates to a radius of 0.3 meters. I get if I round a little bit, 100 radians per second as my angular velocity initial. And if I take my 2 meters per second squared as it relates to that same radius of 0.3, thinking about the fact that it's a slowing down, I'm going to get negative 6.7 radians per second squared. And that's my alpha value. So I can use that omega initial and my alpha to now find some of the quantities that I need. So I don't have time, so the easiest way to do this is going to be using our omega f squared equals omega I squared plus 2 alpha theta, and that'll allow us to find theta, which is the end goal, and then we can think about how many revolutions that is. So if I'm inevitably stopping, that's 0. I now know I started at 100 radians per second. I'm slowing down at a rate of 6.7 radians per second squared, and I'm looking for theta. So when I calculate that out, theta is 750 radians of angle that is being moved through. But so that isn't as helpful if I'm thinking about a tire. What is helpful to know, though, is that if theta is 750 radians, every one spin, every one revolution is 2 pi radians. So knowing that, I can say, well, while the car is braking, the tire goes around 119 times based on the angle or the total angular displacement that the tire moves through.